Hello all, I'm Andrew Kramer, and I will be presenting my work on radar-inertial ego velocity estimation for visually degraded environments. Accurate and reliable state estimates are crucial for any autonomous mobile robot. Visual inertial state estimation is particularly popular due to its applicability to different environments. It can be used indoors and outdoors and requires no external references like GPS and motion capture. Although it is broadly adaptable, there are environments in which visual methods are not usable. Visual inertial methods would be perfectly at home in the scene pictured, but as we move further from the cave's entrance, we can see a problem developing. Visual state estimation methods are severely handicapped in environments without ambient light and other so-called visually degraded environments. That is why we've developed a new state estimation method that is robust to all kinds of visual degradations, including darkness, smoke, fog, and more. Our method uses measurements from millimeter wave radar and an inertial measurement unit to estimate a robot's 3D global frame velocity. Our approach has similar accuracy to other state-of-the-art methods when conditions are optimal for those methods. When visual degradations such as darkness and fog are introduced, other methods falter, but our approach is unaffected. Further, our method uses lightweight sensors with low power requirements, making it an attractive option for small, agile platforms with limited payload and endurance. Several methods for state estimation in visually degraded environments have been presented. If darkness is the only challenge present, LiDAR methods such as LiDAR odometry and mapping work quite well. But LiDAR methods suffer in the presence of airborne particulates such as dust, smoke, and fog. State estimation methods based on thermal imaging have been shown to work well in these conditions. However, there is another sensor type that we feel has not been adequately investigated: millimeter wave radar. Only a few methods have been presented for radar-based state estimation, and these have focused on state estimation in a 2D environment. The most consequential of these are the methods by Sen and Newman. While their work is quite impressive, it is limited to 2D environments, and it relies on a heavy and power-hungry NavTech radar sensor, making it unsuitable for use on microaerial vehicles. Our method, on the other hand, is designed for a 3D environment and uses a lightweight, low-power radar system on a chip paired with a MEMS IMU. The image on the slide shows our sensor rig mounted on a small quad-rotor drone along with an Intel NUC for onboard compute. To understand how our system uses radar measurements, it's necessary to understand a bit about how our radar sensor operates. As shown in the figure, the radar's transmitter sends out a pulse of RF radiation with linearly increasing frequency referred to as a chirp. The chirp reflects off objects in the environment, and the reflections are detected by the radar's receiver. We'll demonstrate how the received signal is processed with this simple 1D example. The radar sensor creates a graph of the amplitude of the return signal over the range from the sensor. The sensor then uses a constant false alarm rate detector to detect the strongest peaks in the range amplitude graph. These detected peaks are returned to the user as a set of point targets parameterized by their range and amplitude. Our sensor uses a more sophisticated version of the same process to return targets parameterized by their range, elevation and azimuth angles, Doppler velocity, and intensity. If we assume the sensor platform is moving and all objects in the scene are stationary, then the velocity of targets in the scene relative to the sensor has equal magnitude and opposite direction to the velocity of the sensor platform. A target's Doppler measurement is the magnitude of the target's velocity projected onto the ray between the sensor and the target. The tangential velocity component is not observed. Because of this, we aren't able to determine the 3D velocity vector of the sensor platform from the Doppler measurement of a single target, but if we have Doppler measurements of many targets distributed throughout the scene, we can regress the velocity of the sensor platform. This leads us to our Doppler sensor model. The true radial velocity, the difference between the Doppler measurement and the Doppler error, is the cross product of the estimated sensor frame velocity and the unit ray between the sensor and the target. It's important to note that the true ray is the difference between the measured ray and the error in the measured ray. This is why the Doppler error term includes the error in the Doppler measurement and the error in the target ray. In this case, the target ray error is both a state to be estimated and an error to be minimized. This is a total least squares formulation for the Doppler error, which considers errors in both the dependent and independent variables of the sensor model. This is in contrast to ordinary least squares, which only considers errors in the dependent variable. Using this constraint, it would be possible to estimate the sensor platform's velocity using only the radar measurements from a single time step, but the characteristics of the radar sensor make this an inadequate solution. The chief problem is with the sensor's measurement of azimuth and elevation angles. The error variance on these measurements are actually dependent on the measurements themselves. Measurements with small azimuth and elevation angles are quite reliable, but these provide little information about the sensor's velocity in the y and z directions. For this, we need radar measurements with larger azimuth and elevation angles, but these measurements are inherently less reliable. So if we only use the Doppler constraint, our velocity estimates in the y and z directions will be significantly less accurate. This is why it's necessary to jointly estimate the system state at several time steps using IMU measurements to constrain the change between adjacent states. In addition to the sensor's global frame velocity, the state vector includes the sensor's attitude and IMU biases in order to accurately compensate for IMU biases in gravity. We estimate these states by minimizing the cost function shown over a sliding window of k successive Doppler measurements using Series Solver. This video shows a typical distribution of radar targets in an indoor scene with the radar targets colored by their Doppler measurement. Notice the points in green. These are illusory readings whose Doppler measurement does not agree with the rest of the points in the scene. There may also be non-stationary objects in the scene, like the person entering from camera left. She produces a large number of red targets whose Doppler reading clearly disagrees with the rest of the scene. If these outliers are not removed, they will significantly affect the state estimate, so we use maximum likelihood sample consensus as an explicit outlier removal step. We compared our method to visual inertial odometry as implemented in the Intel RealSense T265 and LiDAR odometry using a Velodyne VLP16 with the LAMP package. Ground truth was provided by a motion capture system. For these experiments, the sensors were mounted on a hand-carried rig, as shown. We also ran tests in varying densities of fog to test each sensor system's robustness to visually degraded conditions. Fog density was parameterized by visibility distance and varied from 12 meters to less than 6 meters. Ground truth was not available for these tests because fog interferes with motion capture. These plots show errors in the velocity estimates for a typical run with no fog. It is clear from these plots that the accuracy of our radar-inertial method's velocity estimates are on par with other state-of-the-art methods when conditions are favorable. These plots show the state estimates from each method from a typical run in heavy fog. Even though ground truth is not available, we can note that the visual and radar methods often agree, and LiDAR is usually the clear outlier. This suggests LiDAR state estimation is affected by fog to a greater extent than vision or radar. Without ground truth, however, we can't say whether vision or radar were more accurate in these conditions. We also tested our method against VIO and motion capture in dark conditions. These tests show that our system continues to work in darkness, whereas vision does not. Particularly between 50 and 75 seconds, VIO has large deviations from ground truth, while radar doesn't. In this work, we presented a method for estimating the 3D body frame velocity of a radar-inertial sensor platform by fusing radar and inertial measurements. This and a subsequently developed radar obstacle detection method are shown in the video. We can see the radar sensor pose, raw radar returns projected onto images from an onboard camera, and motion primitives from a simple local planner. The mapping method uses the ROS implementation of Octomap with the standard beam sensor model replaced with a custom radar-specific sensor model. Additionally, we have also implemented custom methods for removing multipath reflections and speckle noise. Our results show that our method is comparably accurate to other popular state-of-the-art methods in good conditions. Further, we demonstrate that our method is robust to perceptual degradations like darkness, smoke, and fog, while other methods are severely affected. We are currently working to demonstrate our radar perception pipeline's use in autonomously flying a microaerial vehicle in visually degraded conditions. We're also developing learned methods for improving the performance of our mapping and state estimation pipelines. That is all for now. I'll be happy to answer any questions you may have.